I think this is a problem. Can you hear me? Hello?
Yes, sir.
Yes, sir.
Ah,
Yes, sir.
I got muted. Okay, fine. Let me start. तो ये चल सकता है. Okay, let me start. Okay, so here in the page 131, look at, I want to talk about convergence of sequence. Okay, it's in a topological space. Okay, sequence in X means, recalling, sequence in X, it actually means a function from the set of naturals to X. This n going to Fn, that we denote by Xn. So basically this sequence, but sequence is a function. The sequence in X is actually this kind of function. Now the convergence of sequence, suppose we say what is the meaning of this? Of course, X in X. Its meaning is that for every neighborhood that I defined last time, for every neighborhood u of x, that is for every open set u containing x, this natural number will depend on u. That's why I'm writing this. This will depend. Such that usually we take n naught, but here we are saying this is depends on u, such that xn belongs to u for all n greater than equal to nu. That means if you change u, this will change. But all it means that eventually, that except finitely many members of the sequence, every member of the sequence will be inside the neighborhood. That means eventually it will be in the neighborhood. Eventually, xn is in, that means except finitely many, everybody is here. Now that is the definition of the convergence of a sequence. Now the thing is that in metric space, we have seen that closure point can be in a metric space. Remember, if Xd is a metric space, A is a subset of X, X belongs to X, then X belongs to A bar, if and only if there exists a sequence Xn in A such that Xn converges to X. So this is called the sequential characterization of closure point. But we will see that in general, The sequential characterization of a closure point in a topological space X star may not be possible. Well, you may say this is not a good thing, but the problem is that it is not with the problem is not with the topological space. That is should clear. The problem, I will explain that eventually. Problem is not with topological spaces. The problem is with sequences. Rather, I will say that inadequacy. In the literature, you will find some papers. Inadequacy of sequences. And after I give you the counterexample that I talked last time, also last semester, again I will talk this. That closure point, sequential characterization of closure point is not possible. But after that also, that inadequacy sequences. But that means we need generalization of sequence. We need. And that's the idea of the net. In fact, it's very useful and it's very simple. And eventually I will tell you that how the net idea of net comes. So that is my idea of first net. It's very easy to do it. Okay. The first, let me explain the example that X tau, you take X uncountable tau co-countable topology. That means here the open set tau is X phi union those A such that X minus A is countable. Countable means either it is countably infinite or finite. Countable. Some people call it at most countable. I think Aliprantis Berkinsa called it at most countable. It means either finite or countably infinite. Okay. You can check this is a T1 space by like cofinite topology, but not T2. Any two non-empty open set must intersect, but it's a T1 space because of this thing. Okay. Now here that I proved actually, it's in the which page it is. This is not continuous. I'm coming. Continuous I will talk about later on that. So yes, this is page 135 in my note. Okay. So the counter example I'm talking about. Okay, so that I said here, if you have a convergent sequence in this topology, if it is a convergent sequence, means this xn is eventually constant. Is eventually constant. Eventually constant, which means that there exists n naught if xn goes to x, implies there exists n naught such that xn equal to x for all n greater than equal to n naught, eventually constant. But on the other hand, if you look, since tau is this, x phi union a x minus a is countable. Now look, if you have x uncountable, well, now look, suppose you take an uncountable proper subset. Let a proper subset of x, but uncountable. Okay, right. So what will be a bar? Look, here just see that closed sets here in tau closed sets are x, phi, and countable subsets. Countable, I told you, either finite or countable infinite. So if you take a bar, first of all, it has to be a closed set. Okay. Look, if a was, why I'm taking it is uncountable. If a is countable, itself will be a closed set. So I'm taking uncountable subset that you can always take. The uncountable subset will have a proper uncountable subset. Now a bar, what will be choice? It has to be a closed set. It has to be one of them. Look, since a is uncountable, a bar is also uncountable. So you cannot have this. You cannot have this. So you will have this. Okay. Now, if you take a point outside this, that means x is belongs to a bar. Okay. But sequential characterization not possible, because if you take a sequence xn in a converging to x, okay, that we have got here. That means xn will have to be equal to x for some n greater than equal to n naught. Okay. Particularly, look, xn's are coming from a. If you are assuming, then x will be also in a, but x is outside a. X is outside a. So this is not possible. So this is one example, probably the easiest example. There are many examples. So that sequential characterization of closure point is not possible, because the closures are coming only x here for uncountable set. That is the thing. So that here, this is one example. Make sure that you understand this example. I have written everything carefully here. Okay, that sequential characterization of closure point is not always possible. Okay, right. So that is one thing. That is one thing. Sequential characterization of closure point is not possible. Now come to the point of continuity. Now look, I'm not going to repeat continuity, the definition of continuity. Okay. That remark I did. Now look, page 132. Here also sequential characterization of continuity between metric space is possible, but for general it is not possible. So I want to talk about first, then we'll rectify the situation through NATE. Okay, so that like metric space you are doing it, if you have a function between two topological spaces, definition 3.11, page 132. If you have a function between two topological spaces, these are topological spaces. Take x here, the function value is fx here. So f is said to be continuous. Definition: f is called continuous at x. This is the natural extension of what we got from metric space. If given a neighborhood, that means for any neighborhood, that means open set V, the neighborhood V of fx in y sigma, there exists an open set for that. There exists a neighborhood, that means open set U containing x, U of x, such that if U image is contained in V. This is called the continuity at x. Okay, right? And when f is continuous at each point, if f is continuous at each point of x, then we say that f is continuous on x, or we simply say f is continuous, or just f is continuous. Look, when I say f is continuous means f is continuous at each point. And if f is not continuous on x, whole x, that means you'll have to specify at which point it is continuous and which point it is not continuous. But if I just say f is continuous, that means f is continuous on whole of x. And here, like metric space, okay, that retract I'll do that. Look, theorem 3.3. Theorem 3.3. I have given 4 characterization following A, B, C, D. Okay. But first thing is that there is no hard and fast rule. Depending on the problem, you will choose which one is will be easier to do that. Okay. Though most often uses this, that f inverse v, if we have a function from x tau to y sigma, f inverse v belongs to tau. That means it's open in x for all v belongs to sigma. That means open in this. This is condition B. And this you can use, and its dual result D is f inverse C is closed in x whenever C is closed in y. That means this means inverse image of an open set is open, inverse image of a closed set is closed. Okay. So, but what is that? Is sequential characterization is missing. The sequential characterization is missing. That means in general it is not possible. But later on we'll see that a net characterization is possible, but a sequential characterization is missing. Same example, we will look at it. Look here, what is sequential characterization? Now, you can use this. Now that the example I have given, I think I think here. Yes. On page 136. Okay. Look here, you take identity map from R. This is you are taking co-countable topology. Just now what I discussed, co-countable topology. And here you are taking discrete topology. Okay, first thing you note that tau is strictly weaker than sigma. Here discrete topology, that means anything is an open subset, the open set. Okay, whereas here open sets here, your spaces are here open set is R, phi, and countable subsets of R. Whereas every subset here is open. So like here you see, if you take this thing, sorry, yes, you can take this. Look, this is not open here. This closed interval, not open here, but it is open here. So it is strictly final. Now you take identity map, inverse image of an open set has to be open. So here if you take this thing, open set, this is open here. And I inverse, so I is identity, it will come this, not open in tau. That means identity map is not continuous. Okay. Identity map is not here continuous. Okay. But look, you say I wanted a sequential characterization, but I am going for that. First of all, I am saying here sequential characterization you have, but still the map is not continuous one way. But I can have another example the other way, that map is continuous, still sequential characterization is not there. But here you look, it is not continuous. And what do you have the sequential characterization? Look here, be careful. The I R tau R sigma. Here if you take a sequence converging to X, but we have already seen this is eventually constant. That means xn equal to X for some n greater than equal to n naught. But that means here Ixn equal to xn. So this will be equal to X for all n greater than equal to n naught. Greater than equal to or greater than, it doesn't make a difference. Okay. But any eventually constant sequence is always converges. So this converges in R sigma. That means here this map, identity map, sends convergent sequences to convergent sequence, but still I is not continuous. So that shows sequential characterization of continuity is not possible. But what about this thing? Look, if I take this way, I change I1 R sigma, direction I change. Still it's identity map. Since any open set is open here, so I1 is continuous. Okay. I1 is continuous. But look, here I should tell you that I am going the other direction. Any continuous map if you have, that will always send a convergent sequence to convergent sequence. You can prove straight. So this is expected. If you have a sequence, convergent sequence, which is eventually constant, its image is eventually constant. So it sends convergent sequences to convergent sequence. This happens for any continuous convergent sequence to convergent sequence. So my question in the other direction, that if you have this, whether this will be continuous or not. That the previous example showed. So that you take this as an exercise. Let f x tau y sigma. I'm writing more generally. Be a map. Just write map. X belongs to x. Suppose f is continuous at x. Suppose f is continuous at x. Then whenever xn goes to x in x tau, fxn to fx in y sigma. This is always true. Okay, continuous map will always send convergent sequence to convergent sequence. It's the other direction. If it has happened, sending convergent sequence to convergent sequence, so that it will be continuous or not. That we have already seen. It need not be continuous. That means sequential characterization of continuity is missing. This you should do. This should be easy. So that problem is metric space we have got it. Okay. So metric space you got sequential characterization. These two things, be careful. Characterization of a closure point and B continuity. Okay. But the thing is that I would like to ask a question. Can anybody answer it? That in metric space we got, but have you looked at the proof? Why we got this thing? Why got why? Such sequential characterizations. I'm writing plural means one for closure point, another second one for continuity in a metric space. That is my question. Because unless you understand why you got, then how will you do that? Look, you have two ways to rectify the situation. That if you understand why it got, that either first of all, do really need it to be a metric space or something weaker may work. Okay, that is another thing. Okay, so that first of all, you should in your proof, when you got the characterization, you should look at the proof that where you are using the metric thing. Okay, where you are using metric thing, or whether you are having the using the full strength of metricness. That is the thing. So that one thing, if it is not whole metric thing you work, you can try to have some good topological space, or this is the culprit. You think this. Okay, you can try to replace it by something better. Now look, in metric space, whenever you have a point x, now look why it is working. Now listen to me carefully. You may not understand the full thing now, but eventually you will understand. Here cardinality plays a big role. Now look, when you have x and I have this collection of balls there. N is a natural number. N is a natural number. The first thing, if you take any open set containing U, then by definition of open sets in a metric space, you will get there exists R greater than 0 such that but I can choose N such that choose N such that 1 by N less than R. Then you will be getting this. So ultimately, if you are starting with a neighborhood of X, ultimately you are having this. That means in your argument, you need, whenever you are handling this point X, you need only this collection of neighborhoods. You don't need the entire collection of neighborhoods. Even you don't need this collection of neighborhoods. You need only this collection of neighborhoods. This collection of neighborhoods of X. So that is good enough, because when you are choosing sequence, you remember that you are choosing Xn actually from here. Okay. That is the thing I have told you why we got this thing because of this actually, because ultimately this was good enough. Whenever we are handling with a point on that, this collection of neighborhood was enough, because I told you how it comes this way, but this is countable, and that is also for each such member you are became a member Xn. So look, cardinality of X of a sequence is countable. And this is also countable. This is a countable collection of neighborhoods. Okay, these two are matching cardinality. I'm trying to explain that why it works for the metric space. So that this matching is the only criteria basically you need. That each point you have a collection of neighborhoods countable, then sequence will work. Okay, so he traces two things. First of all, co-countable topology, you will see, look at the neighborhoods at a point. Even if you take this anything like this, you try it, you will never get a countable collection of neighborhoods which will satisfy this. That means for co-countable topology, look, if you take X tau, X uncountable, tau co-countable topology. Here you take any point and take all the neighborhoods. Okay, all the neighborhoods of this. Okay, this is usually we write this NX, this thing. This is the meaning. The family of all now, like metric space, if you try that, you take any U belongs to NX, the countable family. Suppose you do have such a neighborhood, countable family of this. Suppose neighborhoods, the countable family. If you have it, that means given U is a neighborhood of this, there exists N such that this is the question, that X belongs to UN contained in. Look, for metric space I got that was the Bx 1 by N. This is the thing. You will never get it here. You will never get it. You can have a contradiction. If you have it, you'll choose that. I will tell you that in Jan. You will never get it. Okay. If you get it, then sequential characterization will be possible. In fact, in a metric space, you needed this thing, a countable family of neighborhoods around X which will have this property. Okay. And then sequential characterization will work. That means what you are getting. That means, let me tell you. So there is a space called first countable, first of all. So let me define this. Ali Francis Berkinsa is not a book on topology, but you will find, I am telling you, Willard, Stephen Willard, first countable. Stephen Willard. This Indian edition is there, Yale topology. You'll get almost everything there related to topology. And there is another book by Moncrief that you will get, topology. Okay. What is the first countable means? First, of course, you say countable आ गया फिर भी एक adjective है first. Reason is there is another space which is called second countable. That is Ali Francis Berkinsa, they defined in the exercises. So what does it mean first countable? First of all, look what I am doing. Suppose before giving the definition, let me explain that. Suppose you have this, and this is, it's called the neighborhood filter also. Collection of all neighborhoods. Say it, family of that is the reason. This is called the neighborhood filter. At X. Now suppose there is a countable subfamily. UN, N belongs to N of an X. That means you are having a collection of neighborhoods, but countable, such that whenever U belongs to an X, there exists N such that I have this. This even will depend on U. So there exists N. Okay, that finally that means I will be able to work with this thing, this family. Okay, this is a countable family. You may have, may not have. Suppose you have it. In metric space we have. Exactly metric space we have. We have all the balls like this. Here UN is actually is this. If you have this, then you say that it is first countable at X. You say that it is first countable at X. It is first countable at X. And like continuity, if it is happens first countable at each point, if it is first countable at each point of big X, then we say that X tau is first countable. I'm going to write formally is first countable. Look, in your proof, Now, if you look at the proof of the metric space, that what you need this much actually. So, by my definition, every metric space is first countable. So that let me write first. Let right now I need only for first countable. I don't need to worry about first countable at X. That I more generally I did. It may be first countable at some point and not at some point. But I will generally will deal with only first countable. Let, so I'm writing let X tau be a topological space. Okay, topological space, and if for each X belongs to X, suppose, actually write rather suppose for each X belongs to X, there exists a countable subfamily here. I am writing just to power, not to indicate n. Uxn, n belongs to n. Suppose for each X belongs to X, there exists a countable subfamily. This to indicate that it will depend for X, that if you change X, it will change. This family will change. This is the neighborhood filter at all, collection of all neighborhoods at X. Okay. Such that whenever U belongs to NX, there exists N belongs to N such that this is the obviously will be true. Actually, if you are not confused, then you can erase this thing. But you should know that it will depend on X. Suppose for each X there exists a countable subfamily UN of this. I'm saying. So it is good enough because NX says that whenever U belongs to N, there exists such that you have this. Suppose you have for each X you have. Okay. Of course, this will be changed because this will change. Okay. Suppose you have it. Then we say that then X tau is called first countable or a first countable space. So that example, every metric space is first countable. Your tutorial teacher will be Saurabh Sarkar. He is a very bright scholar. He is working with Biplab Boshak. So he will fix your this thing. Saurabh Sarkar. I taught him operator theory. So he is very bright. He will teach you. He's working in combinatorial topology. So, but he is good in both topology and analysis. Okay, so that he will fix the tutorial time with you. Now here, why I'm saying exercise, I'm giving it. Can you guess what exercise I want to give? Every metric space is first countable, but that is a weaker condition. So I want to give an example of a space. Give an example of a first countable space first countable space which is not a metric space. This is the thing. Now look, the proofs of metric space we have taken. So if you take first countable space, that I want to give you the exercise. The sequential characterization of closure point will be possible. Sequential characterization of continuity will be possible. But still look, we are putting some condition on the topological space. But I will like without any such condition. That's another approach. The sequence has to be replaced. So that first countable space. So that this results also exercise I'm putting. Okay, I think better you put result 1. Let x tau be a first countable space. A subset of x, x belongs to x. Then x belongs to a bar if and only if there exists a sequence xn in A such that xn goes to x in x. Okay. And result 2, I'm writing this way, but you should be careful. You should be able to prove it, and then you see where you are using. Let x tau first I'm writing the simpler version. Be a map between two first countable spaces. I am taking both x and y first countable spaces. And x belongs to x. Then f is continuous at x if and only if whenever xn goes to x, this x is here in x tau, fxn goes to fx in y sigma. I told you continuous, it's then one direction, it is always true actually. That if it is continuous, then it will send convergent sequences to convergent sequences with the other direction here. That means if you have this, then to show that f has to be continuous at x. Okay. You can look at the proof of the metric space, how we proved that this way. Same proof will work here. Instead of bx y1 you will be replacing by un. Okay. That is the thing you should look to your exercise. Of course, you can find in many books that as results and the like we learned. But here I would like to mention, do you need both to be first countable? That you should check whether you need this to be first countable. You look at the proof of what I got for metric space. Okay, if that proof doesn't require one side to metric space and that, then you can do that. So that you think about that whether you need both to be first countable. Okay, so these two results says if you work in the domain in the collection of first countable spaces, then sequential characterization of continuity and closure points are possible. So that these two exercises, I would like to show you that how you argue that this thing x tau, you're taking first infinite and this is cofinite topology, whether this is first countable. So it is not discrete. Discrete space is first countable. Okay, so that's why it is not discrete. Is first countable. Okay, right. Well, before that, let me tell you this thing. Okay, I will do that. But before that, suppose you have a topological space. Don't confuse with that. Suppose you have a topological space, T1 space. Suppose you have T1 space and U is open. Then for any point, look, U minus X, it is written as, can be written as since it is T1 space, means every singleton is closed. That means this is open. This whole thing is open. This is open. That means this is open. But you need T1 space. Okay. So if you have T1 space, now look, the first countable space, you have taken this. Suppose you have at the point X, you have that UN. Then what will happen? Look, X is everywhere. Okay. So it will contain X, but I am saying this is X. If X tau is a first countable T1 space. Okay. Got it? First countable T1 space. Okay. Why? Well, let me, the simple thing. Suppose X tau is a first countable T1 space. That's why indiscrete space works as a counterexample. That is not a T1 space if it contains more than one point. First countable T1 space. And let X belongs to X. And this is called the basic neighborhood. So I can write, suppose such that for each U belongs to NX, there exists N such that basically I am taking first countable at X, that I am saying, but I am specifying which I am taking. Then this has to be okay. Look, this is X is belongs everywhere, all events, so this is true. Okay. Now look, why only X will be there? Because look, UN minus X. Suppose not that exactly. Suppose you have another point here. Y belongs to this and y not equal to x. Okay, right? Got it? Okay, fine. Then take a neighborhood u of x, right? So u minus y, look, y not equal to x. So x belongs here. Also, what I explained, this is because it's Q1 space. So this is open. So this is an open set containing x. That means it belongs here. Okay, right? So since it is first countable at x, there exists n such that when I don't need that. I could took any point other than x. Okay. Actually, I don't need this thing. Choose any y. Basically, choose y doesn't. What I'm going to show that if you have y different from x, that won't belong here. Why? Because this will be a neighborhood of x, this u minus y. And since it is because of this condition, there will exist n such that. But at least one even is getting which doesn't contain y. So that it will won't contain y. You are getting at least one n here, un, which doesn't contain y. Because un is, look, subset of this. So that you must have x. Okay. The first countable T1 space. Okay. But you may, okay. Now look what I will use here. First take the easy thing that x tau take uncountable, because we are working with this topology, tau co-countable. Okay. I'm saying it is not first countable at any point. Choose a point x belongs to x. If possible, suppose x tau is first countable at x. X I have chosen arbitrarily. Okay, so there exists a family of neighborhoods satisfying this. Okay, right? Which satisfies the condition of first countability. And look, we have already proved this is a T1 space. This is a T1 space because every point is closed here. So intersection of un, n belongs to n, is x. Now look, x minus intersection un by De Morgan's law, this is x. So this is x minus cofinite topology. Still you need uncountable. I'm telling you why. Now look, each un is open actually in x tau, so that this is countable by the definition of open sets. Each x minus un is countable, but countable union of countable sets, last semester I taught you, is countable. It may be uncountable infinite because this is countable. Okay? That means right hand side, countable union of countable sets, you are getting countable. But here, you have taken x uncountable. So you are only deleting one point. So this is uncountable. समझ गया? This is countable. You are getting contradiction. Left side you are getting uncountable. Right side you are getting countable. Uncountable contradiction. So that not first countable. That is the one reason that it was happening. It is not first countable at any point. Okay. That sequential characterization was not possible. Okay. Got it. So make sure I'm leaving it now. So next Friday, coming Friday, I will take the class. Okay. So that exercise that try to understand we say that first countability. If you understand this, you will understand the basics of topology and then do the exercises which I mentioned. Okay. Because after that, I'll go for net. Okay. But at least you see that first countable. Make sure that you think of an example of a first countable space which is not a metric space. Which is not a metric space. ठीक है? Okay, see you. I will meet you on Friday. Okay.
Thank you, sir.
Thank you, sir. Have a good day.
Thank you. গড়বড় করে ফেললো।